Good morning. Today we are going to calculate the expression for the power required in the blade element theory using for forward flight of helicopter. We start by calculating the rotor profile drag and the rotor drag power. If you remember, we demonstrated that the rotor profile drag power is the power required to overcome the blade's aerodynamic drag force due to friction, and it was an integral from the drag force along the radius and along the azimuth multiplied by the number of blades divided by 2 pi. On the other hand, the rotor drag power was the power required to overcome the difference in profile drag forces between the advancing and retreating side, and it was due to the so-called H0 force. We will start first calculating the rotor profile drag power. How to calculate this integral? First, we have to calculate the profile drag of the blades. Now, the profile drag of the blades is classically defined as rho over 2 v square, the profile drag coefficient, multiplied by the area of the blade element. If you remember, the velocity at the blade element can be approximated with the tangential component of the velocity, which is omega r plus v cosine of alpha disk sinus sub c. In this way, we can substitute the drag force into the integral and try to perform this integral along the radius. This integral can be solved. How? Usually is done by non-dimensionalizing the parameters in this integral. One of the most important definitions for forward flight is the definition of the advance ratio. Advance ratio is defined as the ratio of the v cosine of alpha disk, the tangential component of the velocity vector, divided by omega r. For forward flight, of course, it is usually approximated with v over omega r. The advance ratio of any helicopter is in between 0 and 0.35. And this shows that we can divide more classes of helicopter and assume the advance ratio in those classes. Now, substituting in the integral the profile drag power, the definition of the advance ratio, and using the non-dimensionalized notation for the rotor radius, x, and recalling the blade solidity, sigma, it results in an integral on x which can be easily integrated. Finally, performing the integration, we arrived at the expression of the rotor profile drag power as the rotor profile drag power in hover multiplied by 1 plus squared of mu, advance ratio. We go now to the rotor drag power. Now the rotor drag power, it was the power coming from the H0 force. This formula can be also expressed as a function of the advance ratio, so that we have first to calculate the H0 force on the rotor. How to calculate the H0 force on the rotor? Now, if you remember, the H0 force was also due to the profile drag, the component which is with sinus c and cosine phi. In this way, integrated from 0 to r, integrated along the radius, multiplied it by the number of blades divided by 2 pi, it will result in the integral, the H0 force. Going back to the rotor drag power and performing the integral, we will obtain that the rotor drag power is the is a function of the squared mu, the squared power of the advance ratio. Now, adding the rotor profile drag and the drag power, it gives us a formula which depends on 1 plus 3 times the squared of the advance ratio. Usually, this value is underestimated. Bennett proposed experimentally a correction using a factor 4.65 in place of 3. So we have the Bennett approximation, which gives us the power which comes from the profile drag and the drag of the blades, which is profile power drag in hover multiplied by 1 plus 4.65 squared of the advance ratio. How to determine the medium drag coefficient? Usually, the medium drag coefficient can be determined graphically using this CL variation, medium lift coefficient, as a function of the medium drag coefficient. If you recall the blade element theory and that we demonstrated that the medium lift coefficient can be easily calculated as 6.6 CT over sigma, approximating CT with the weight coefficient, non-dimensional weight coefficient, it gives us a value of the medium lift coefficient, knowing the Mach tip number and the value of the K, which gives us the non-uniformity of the induced velocity on the blade, will result in the medium value of the CDP, of the drag coefficient. Let's continue now with the induced power. Induced power is the power required to overcome the induced drag force. If you remember, we said that this is an integral from the induced velocity dt and then along the radius, along the azimuth, and multiplied by the number of blades. However, we said that this integral cannot be calculated as the induced velocity is not uniform along the rotor. Usually, we take the K coefficient to account for the non-uniformity of the blades so that finally the induced power in forward flight is calculated exactly as in the hovering flight as KTVI. This power is the power required to move a mass of flow through the rotor disc at an induced velocity. We can see that as the helicopter it goes faster, actually the rotor needs to do less work as the induced power is decreasing. At high speeds, this induced power is just a quarter of the induced power in hover. Next, the K factor, it varies for the induced power calculation with the velocity of the forward flight. In high forward speed flight, we have a K of 2, while in a low speed flight, we have a K of 0.5. And the non-uniform induced distribution, we showed that it involves also the upwash in front of the wing. Next, let's calculate the fuselage parasite drag power. The parasite drag power is the power required to overcome the drag of all aircraft except the rotor blades. As any power, it is the drag force of the fuselage multiplied by the velocity. We assume as the fuselage as an equivalent flat plate drag area. And we have to calculate this equivalent flat plate area in order to obtain the parasite power. How to calculate this? Usually this is done statistically using the helicopter gross weight. Here you see one graph of giving the equivalent flat plate area as a function of gross weight. The equivalent flat plate area is defined as a fixture body having a frontal area of 1 feet and a drag coefficient CD equals 1. You see two lines of one for the clean helicopters like the Lynx helicopter and one line for the utility helicopters. Knowing the gross weight of a helicopter gives easily the equivalent flat plate area of the helicopter you are using. The parasite drag area at helicopters is much higher than the one of the airplanes. In an airplane, the equivalent flat plate area is between 1 to 10 feet square. In an helicopter, it goes from 5 to 100. For example, you see here the components of the helicopter producing a drag. For example, the fuselage and the engine nacelles produce the most. The rotor hubs are coming on the second place. The landing gear, the empennage, and then a general miscellaneous power, a miscellaneous drag. Now, if we finally sum all these powers, we obtain the total power required in forward flight as induced power plus rotor parasite power plus the rotor profile drag power plus the fuselage drag power and plus losses due to the tail rotor, gearboxes, hydraulic pumps or electrical generators. This miscellaneous power is usually 3 to 6% from the power required for the rotor. Substituting in this summation the values that we just derived of the integrals result in a simple formula which involves the advance ratio, the thrust of the helicopter, induced velocity, the medium drag coefficient and the flat plate area. Therefore, we can represent the power required as a function of forward speed. One can see that the induced power dominates in hover and is decreasing as we are flying faster. The parasite power is very small in hover but is increasing as we are flying faster. The profile drag power, it is slowly increasing with the velocity. One will obtain the so-called bucket shape of the required power, where we see that the required power is high in hover, is falling to a minimum at a moderate speed, and then is rising again at high speeds. So this is the so-called bucket shape. The best speeds that can be defined in this curve are point A is defined by the minimum power and corresponds to the speed for best endurance, loiter time. Also, it corresponds to the minimum rate of descent in auto-rotation. And the correction A prim is the parasite drag is increased appreciably in climbing. The point B is defined as tangent to the curve and corresponds to the speed for best maximum range. This ends the demonstration of the power required in forward flight plus the best speeds.